Hi, I'm Reyne from the University of Sydney, and I'll be going through practice problem sample R. Now, as I have done before, the first thing I'm going to do is look at these tests. So the tests are a really good way to rule out or narrow down what we're looking for. So straight off the bat, we can see that there is no unsaturation. There's no reaction with bromine. There's been nothing oxidized. We don't see any reaction by adding potassium dichromate, acidified. But we do see bubbles of carbon dioxide when we test for a carboxylic acid using sodium carbonate. So that tells us that there must be a carboxylic acid present. This is great news. It helps to narrow down things really quickly. Now, as before, I'm going to skip IR and mass spec in preference of trying to narrow things down with the carbon and the proton first, and then I'll confirm some of those initial ideas we have by coming back to these. So in our carbon NMR, we can see a total of 5 peaks. So let's label these up. We've got 1, 2, 3, 4, 5. And this is a really distinctive sort of pattern to see. We can see that peak 1 is way down at about 180 ppm. Now, if we recall what that means to be downshifted so far, that relates to the idea that that carbon environment is being hit or is right next to a couple of quite electronegative species. Now, we've already established that there's a carboxylic acid present. So I'm going to bet that this is the carbon in the middle of that carboxylic acid, okay? And then when we look at peaks 2 through 5, right, 2, 3, and 4, and 5, we can almost see they're gradually moving closer and closer to a lower ppm. Now, this to me suggests that we are likely looking at a straight chain of carbons. So if we think about the effect of that carboxylic acid, it's pulling electron density away from that first carbon, and there's a flow-on effect that weakens each carbon you move away. Now, we're going to have to look at more information to confirm that, but that's my first kind of thought. We can also see that all the heights of these peaks are similar. Now, in a carbon NMR, we can loosely compare heights to give us an idea of the ratio, and this would also support that idea. If we head down to our proton NMR, we can now see a total of, it's a bit hard to zoom in, we can see 5 different proton environments. We can see, and I'll label these A through E. You can see A, we've got a singlet, we've got a triplet at peak B, which is just above 2. I'm going to label the zoomed in version that's kind of inset into the page. We then have a quintet at C. We then have a, what's that? I've forgotten the word for it. Sextet, 6 peaks. We've got D, and then we've got a triplet at E, okay? And similar to what we saw in the carbon NMR, those 4 peaks, B, C, D, and E, are quite close to 0. They're kind of in between 0 and 2, which is suggesting to us that they are far away from something that's de-shielding them. Whereas the singlet up at A is actually very, very, very de-shielded. So it's up at about 12 ppm, okay? So we'll come back to that one in a moment. Now, when we look at the peak data table down the bottom, so this is where we can kind of really start to pull out some more information about the integrated area under these peaks, so the peak area ratio. We can see that our singlet, so peak A, only has 1 signal, and then we've got a lot of 2, 2, 2, and 3. Now, this should hopefully be starting to kind of trigger some ideas for you that maybe once again, we've got something like a single chain that's indicating that we've got similar sort of proton environments that differ in terms of their placement, but the area of those ratios are kind of quite similar. There are 2 protons in that environment. There are 2 protons in this environment. So that one, there are 2 protons in this environment and 3 protons in that environment. The number of peaks then tells us a bit about how many protons are next to it, okay? So there's the n+1 rule, and that really relates to how many neighboring proton environments and how many protons in those environments are present. So we might leave that because that will work best for us when we start trying to draw this out. And we'll come back up to then the mass spec. Now the mass spec here is at 102. And as I've done before, I'm going to take the simplest ratio of the carbon and proton NMR. So just because there are 5 signals doesn't mean that there are 5 carbons. There could be 10 carbons or 15 carbons, but I'm going to assume that there are 5, and I'm going to work off of that first. So let's say that there are 5 carbons, which would give us a total of 60 towards that mass to charge ratio, molecular ion. If we think about our protons, we're adding up the number of protons present using the peak area ratio. That suggests to me that there is a total of 10 protons, which brings us to 70. And we know that there's a carboxylic acid, so there must be 2 oxygens. And look at that. Whoops, sorry. Let's just write this out properly. So 10, 32, and then all of those together add up to 102. So that's looking great. So our assumption that there were 5 carbons and 10 hydrogens was spot on. If we want to kind of maybe confirm that there's a carboxylic acid present, we can kind of come up to our IR to look at some of this. And this one's a bit trickier. So first of all, I can see this really distinctive peak at about 1700. That's going to be our carbonyl. So that's an easy one to pick out if it's present. We then have what looks like a bit of a mess. And I reckon what's in here, now I might color code this, is that we've got a broad OH peak at about the, I don't know, 3300-ish sort of space. But if I change to red, I reckon that we also have the C to H stretch at about the 3000 mark as well. And we would expect to see that. It's got a hydrocarbon there. And again, we can see that peak at about the 1450 here, which would be the C to H bend peak as well. So really the IR here doesn't tell us heaps, but it does confirm what we were kind of suspecting. It tells us that there is indeed a carboxylic acid through the combination of that OH, the broad OH peak, and the carbonyl peak. So let's start putting this together. So it really is the shape of this carbon NMR is really what's making me think that it's a straight chain. Okay, so let's just maybe start with that idea first. Let's first of all draw our carboxylic acid like so at the end. It has to be terminal because there's no way for the carbon to have more than one bond. And then let's just draw out. We got 1, 2, 3, 4, 5 carbons. Okay, 5 carbon environments, 5 carbons. Now, if I start to color code these, well, our most deshielded carbon has to be this one. Well, has to be that one there in the center of that carboxylic acid. And then, as I said before, we can almost think of the flow-on effect of that electronegative deshielding of the carboxylic acid to kind of suggest that, well, that's probably going to be 2, 3, 4, and 5. As we move further and further away, the influence of those electronegative oxygens will decrease. In terms of the proton environments, we can kind of do the same. And here is maybe where we can think about the number of peaks that we observe. Now, the singlet up at about 12 ppm, I reckon, is going to be this proton on the carboxylic acid. So similar to an alcohol, we tend to see a singlet because they don't interact. So it's going to be kind of a loner of its own, okay? Now, we also saw a few different types of multiplicity. So we saw a triplet, we saw a quintet, we saw a sextet, and then we also saw a triplet. Now, in the case of, maybe if we start with the terminal, so carbon environment number 5, we have 3 hydrogens in that terminal carbon, and the only thing next to it is going to be that carbon at carbon environment 4, which only has 2 hydrogens. So to me, this would be the least d-shielded. It matches the triplet of peak E. Okay. If we want to think about where is the other triplet, so peak B was another triplet, but this one is relatively more d-shielded than the others. Well, I reckon that's probably going to be here. I reckon it's going to be carbon environment 2, because it's the closest one to our carboxylic acid, and there's no hydrogens at carbon C, not carbon C, carbon 1, sorry. And at carbon environment 3, we know there must be 2 hydrogens if we're assuming that it's a straight chain. So this would mean that this is going to be C and that we're going to be D. If we think about carbon environment C, it's got a quintet by 5 spikes in our peak. So the n+1 rule would state that it needs to have 4 hydrogens around it. And if you look on either side of that carbon environment 3, they're both going to have 2 hydrogens. Total of 4 explains the splitting of 5. If we look at carbon environment 4, so proton environment D, it has a sextet. So 6 spikes, the n+1 rule, must be 5 hydrogens around it, where there's going to be 3 on the terminal carbon next to it, and there'll be 2 at carbon environment 3. That matches up as well. So this is all pretty good. This is confirming a lot of what we worked out throughout the way. So the last thing to do is to name this. We would name this pentanoic acid. And we're done. Cheers.